All right, welcome back. This is, let's see, 1-3 that we're on now, as far as videos go. And today we're going to talk about density, and we'll add a little bit more about dimensional analysis. Once we have density as a unit, we can see how density works as far as dimensional analysis. So density. Density is a value that describes how much mass is present in a volume of matter. So it's kind of a way of saying it's how much mass is crammed into a particular amount of space. So the formula for density is actually really easy. It is mass over volume. And by over, I mean mass divided by volume. So in terms of SI units, you could think of this in terms of, typically it's going to be something like grams over liters or milliliters, some unit of volume on the bottom and some unit of mass on the top. There's a little trick that I remember that helps me to recall the formula for density, and I think of density as a heart. So if we draw a heart, and we put a line right across the middle right there. There's our dividing line, right? And if we look at this, this is an M. And on the bottom, we have a V. So mass over volume with a line in between. So just a trick for remembering the formula of density. Now, the next thing about density that I want you to understand is that each type of matter has its own specific density. So that means that we can use density to actually identify a substance. If you're not sure what a substance is, if you have an unknown block of something, or you're walking down the street and you find a weird chunk of some element and you're pretty sure it's, or some substance, and you're pretty sure it's pure or relatively pure, you want to find out what it's made out of, you can figure out the density. The only thing you would need would be the mass and the volume. So take the mass over volume, you'll get a particular number, and then you could compare it to known densities. For instance, water has a density of 0.997. Ethanol has a density of 0.789. And what that means is that for every gram of ethanol, for every mass of ethanol, it's going to have a particular volume. So gram of ethanol will have a volume of about 0.789 grams per milliliter. So units here, grams per ml. I have naked numbers, and we're not supposed to, right? So I apologize for that. So ethanol, 0.789, aluminum, 2.699. What does that tell us? Well, that tells us that if we were to arrange these densities in order, we would see that aluminum has the highest density of the three. In the middle is water, and then having a slightly less density than water would be ethanol. Ethanol is an alcohol. So we have those three, and they're arranged in terms of density. Now, if we were to take a cup, right, and we were to put some water in here, what we would see is if we put a little chunk of aluminum in, it would sink to the bottom because it has a higher density than water. Ethanol, on the other hand, would sit on top, because ethanol has a density less than water. So you can actually look at densities. Sometimes you can figure out, I guess, relative densities by comparing substances and how they float compared to water. So if something sinks in water, that tells you the density is greater than water. If something floats on water, it has a density of less than water. Just kind of a weird random fact or side tangent. So if we continue down the list here, notice iron is far more dense than aluminum, 7.86 compared to 2.699. Gold, look at this, 19.3. Very, very high density. So you can use, or gold rather, will have a very, very high mass compared to the volume. And if you think about it, it kind of makes sense, because things like water's kind of heavy, but you would think of a small block of water, small ice cube, would have, would be liftable, right? No problems lifting ice cubes. But if I were to give you a block of iron the same size, it would be much, much heavier. It would have more mass packed into the same amount of volume. If I were to give you an identical size cube of gold, it has an even higher density, more than twice that of iron. So that little block of gold would have a mass of more than double the mass of the iron block with the same volume. Again, it's a way that we can identify substances, tells us about how much mass or how much matter is in a particular amount of space. So this means that density is what we call a physical property. You can measure the density without changing the chemical properties of the substance. We can look at different substances, we can calculate their densities without changing them. Meaning I can find the mass of a block of gold and I can find the volume of a block of gold, and it still is a block of gold. I haven't changed it into something else. So, and we also, as we said, density, we said this actually a couple videos ago, density relates to different quantities. It relates mass and volume. So it's a way of actually looking at two different types of measurements, one that deals with the amount of matter and one that deals with the amount of space. All right, so let's talk about how density relates to dimensional analysis. And really, the only thing is that density deals with two different units, like we just mentioned. So when you're doing dimensional analysis, we have to add one extra rule. And our extra rule is right here. The new extra rule is just that we deal with 1 unit at a time. Okay? Density has 2 units, so we deal with 1 unit at a time. Let's take a look down here. Here's our practice problem. A substance has a density of 4 grams per liter, but you need the density in kilograms per milliliter. So they gave you one set, but you really need it in this version for whatever reason. Okay? We can do this. We can use our dimensional analysis to convert these units over. All right? The only thing we need to do is focus on 1 unit at a time. So let's start with mass. We were given 4 grams per liter. Okay, and we're going to start with the grams, the mass that's on top. Just like any other dimensional analysis problem, we start off with a dot and a line. We have the units. These are the units that we have. We're going to put those on the bottom because we're following the normal 4 rules. And one of the rules states that you have to set up the units so that they cancel out. Okay. Now, what equality or what conversion factor do we want to use here to get to kilograms? Well, let's think about this. We have grams. We want to get to kilograms. Okay. Do we have a number that relates those? We do. If you remember KBM, right? Killed by math. 1 kilo equals 1,000 base units. 1 base unit equals 1,000 millis. And remember, if you're going to the right, you multiply. If you're going to the left, you divide. Okay? Grams fits right here. It's a base unit. And we want kilos, just right here. So we are going to the left, so in fact we are going to divide. That means, if we look up here, grams would plug in right here, right? It's a base unit. Just above it is the equality relating kilo to grams. Okay, so it's 1,000 grams to 1 kilogram, right? 1 kilogram. Okay. What that's going to do is it's going to cancel out our grams. And if I'm just dealing with this 1 unit, I can go ahead and do my math here. So 4 times 1 divided by 1,000. Okay, 4 divided by 1,000. Remember the trick? Find your decimal spot. We have 3 zeros here, so that means our zeros are going to move 1, 2, 3 spots to the left. Okay, our decimal moves 3 spots to the left. So we're going to have 0.004. Now we need units. Remember, no naked numbers. No naked numbers. So we look over here. We have kilograms. That didn't cancel out. And we have our liters still. So we need to put our liters back in here. Okay, there we go. So right now we have 0.004 kilograms per liter. That's 1 unit down. But we have 2 units. We need to convert liters into milliliters. Do we have an equality that relates that? Yes, we do. We go back up here to KBM. Liters is a base unit. Milliliters is milli. So we have liters, the base unit. We want milli, so we're going to the right, which means we're actually going to multiply now. Okay. Let's just write out the equality so we're clear on this. We have liters, right? We know that it's 1 liter for every, and we're going to milli, right? So that's 1,000 milliliters. Okay, so 1 liter equals 1,000 milliliters. So let's set it up, dot line. Now, this is where there's a little tricky thing here. Liters is on the bottom, right? And the rule that we had back in dimensional analysis always said that you set it up so the units will cancel. So we actually have to do this setup over here, opposite what we would normally do. Since we have liters on the bottom and we want liters to cancel out, over here we have to put our 1 liter on top. That way we still have liters divided by liters, they're still going to disappear. Opposite the liter, you're going to plug in your 1,000 milliliters. So they get plugged in here. Okay, liters have canceled out. We're going to end up with kilograms divided by milliliters. Notice that's exactly what we want. So now we have 0.004 times 1 divided by 1,000. So here we go. Our decimal is right here. We're dividing by 1,000, which means our decimal is going to move 1, 2, 3 spots to the left. So we'll end up with 0.0000004 kilograms per milliliter. Okay, really tiny number. Really tiny number, but that's the answer. Okay, so the key here again is 1 unit at a time, and that's as difficult as it's going to get right now for dimensional analysis. All right, here's another practice problem. I want you to do this one right now. Pause the video, set it up, do it right now, and then unpause and check your solution. Pausing? Okay, so we are going from 4 kilograms to milligrams, right? Kilograms to milligrams. Well, if we remember back, kbm, that means that we are starting here, right? We're starting with kilo, and we need to go to milli, okay? That's where we're going. So we actually need to go from kilo to the base to the milli, all right? And then notice with the other units, we're going from meters to centimeters. Ooh, centi, that was our like 4th unit, right? That was our 4th one. So if we remember, the base unit, 1 base, equals 100 centimeters. So that will be our equality there. Here, it's 1 kilo equals 1,000 base, and we know that 1 base equals 1,000 millis. Okay, so let's get going here. All right, 1 unit at a time. Let's start with mass. Okay, so 4 kilograms per meter, right? And we know that we need to go from kilograms to grams to milligrams, right? So let's set it up that way. We have kilograms right now. That means kilograms needs to go on the bottom. We can't go straight from kilograms to milligrams. We have to go through grams first. So grams are going to go on top. Okay. To plug in these numbers, we can go up to kbm. Notice it's 1 kilo for every 1,000 grams, for every 1,000 base units. So the 1,000 goes next to the base unit, goes next to the grams, and the 1 goes next to kilo. So 1 down here. Then we go on to our second part. Okay, so far we've canceled out kilograms. These are canceling out. Kilograms divided by kilograms. We have grams right now, right? We want to go to milligrams. So we are going to get grams to cancel out by putting it on the bottom, right? Because grams divided by grams will cancel out. And then we want to relate that to milligrams, which we'll put on top, just like that. What numbers do we plug in here? Well, go up to kbm. It's 1 base unit for every 1,000 millis. Grams is the base unit, so it's 1 base unit for every 1,000 millis. All right? That deals with our mass. We've canceled out the kilograms, we've canceled out the grams, we're left with milligrams. And those, in fact, are the units of mass that we want. So let's do the math for that. That's 4 times 1,000 times 1,000. So basically, it's a 4 with 6 zeros after it. Is that enough? Yes. And don't forget your units, milligrams, and don't forget this guy over here, meters. So that's 4 million milligrams per meter. Is that what we want? No, right? We still haven't changed the other unit yet. We need to change the length. So we're gonna rewrite our little answer there, our 4 million milligrams per meter, and we are now going to use dimensional analysis to change this bottom unit. Okay, just like before. Now, I reminded you that 100 centis equals a base unit. So let's see. Meters, that's the base unit, right? The trick is when you're dealing with units on the bottom, they need to cancel out. They need to be opposite or diagonal each other, right? So we know meters has to go up top in order for the meters to cancel out. And we want the new units on the bottom to be centimeters. To plug in these numbers, we go to our equality up here. This is one that we said we needed to know. So it's 1 base. The base is the meters, right? And 100 centimeters. Okay, so if we look at this, we have 4 million times 1 divided by 100. Neat little trick with zeros. If you ever have a number like this with lots of zeros in it, and you're dividing by a factor of 10, in this case 100, count up the zeros that are in this. There's 2 zeros. You can cancel those out on the top and the bottom. So now we've just got, what is that, 40,000 times 1 divided by 1. So we're left with 40,000, and it is, what's our units here? Milligrams over centimeters. Okay, so as usual, my writing's a little angular. Sorry about that, but that's how it works, right? Those are our practice problems. You have your next set of practice problems for the class. You can go ahead and get started on those. I'll be able to answer questions on it tomorrow, and we'll see you then.